Hi all. All right. So I think I said in the last review video that once you start zooming out and looking at our galaxy and other galaxies, the distances become much bigger than what we've been talking about in the semester so far. Um, our whole galaxy it's big. It's got hundreds of billions of stars. It's 30,000 parsecs in diameter, and yet our galaxy is just one. The nearest galaxy over, which we don't have in a picture here, is 2 million light years away, about 750,000, right? Isn't that 750,000 parsecs away, right? Which means that the sizes of galaxies, once we've zoomed out to this point, the sizes of galaxies become small compared to the huge distances between them. If memory serves, this is the Triangulum galaxy, which is the other major galaxy in the local group, right? The Milky Way, Andromeda, and Triangulum are the three major galaxies in our local group of galaxies. And so you're looking at multiple spiral galaxies, right? You realize, okay, spiral galaxies have a lot of the same features. They've got the bright bulge at the center. They've got the spiral disk with the dust lanes and the stars. They've got stars out there in the halo, globular clusters out there in the halo. And even though every spiral galaxy looks a little different, they have a lot of the same features in common. As opposed to elliptical galaxies, right? They're very different from elliptical galaxies, which are just big balls of stars. No disk, no dust, very little dust. Just a big ball of stars all orbiting around each other. Irregular galaxies are called that because they don't have a nice regular geometry to them, right? Spiral galaxies, elliptical galaxies, at least are mostly symmetrical, right? If there's any galaxy that is sort of lumpy, random-looking, asymmetrical, then we generally categorize them as irregular. They tend to have lots of gas, lots of star formation, young stars. Most of the time, because whatever process influenced this galaxy, whatever process warped, pushed, pulled, whatever process made the galaxy become irregular, tends to also agitate the gas and compress the gas and trigger a burst of star formation. Sometimes, but not always. So that's why irregular galaxies really are sort of the really interesting ones, because something weird's going on, and it's fun to try to figure out what. So let's see. Okay, we got galaxies A, B, C. How can we classify these, and how can we use the pictures that we see to figure out what's going on with these galaxies? Which one is a spiral? Okay, galaxy C is the spiral. Which one's elliptical? A is the elliptical. B is the one that is lumpy, irregular. There's star formation. There's star formation in the... I keep, this is probably hard to see. Okay, right? There's star formation happening in the spiral galaxy. There's star formation happening in the irregular galaxy. One of the telltale signs of an irregular galaxy is that where the stars and the dust are doesn't always line up nicely with where the star formation's happening, right? In a spiral galaxy, it's all happening in the disk, right? The dust, the gas, the star formation, the young stars, they're all together in the disk. In an irregular galaxy, rather, right? The stars and the dust and the gas and the star formation and the young stars can all be kind of jumbled in, not in a nice regular pattern. So if you see that, okay, probably irregular. Which ones have active star formation? Well, how can you tell? Look for the star-forming nebula. And you know that you're seeing a star-forming nebula Because what are stars born out of? Well, stars are born out of nebula, and what is that nebula made out of? Mostly hydrogen and helium. So if you see a big blob of red, like those there, this probably isn't showing up as well on on the video, but hopefully it looks better on your paper, right? The red blobs there, there, or the red blotches. Okay, I'm seeing a lot of blue, but okay, that looks like a bit of a pinkish blob there. So there's a few back there, right? What are the red blobs? Those red blobs are hot, glowing hydrogen, right? Hydrogen has that bright red emission line. And so if you see a blob of glowing red gas, that's a good indication that that blob of red is hot hydrogen. What's heating up the hydrogen is the luminosity of newborn stars inside of the gas. And so when you see that, that's a good indication that that's an active star-forming region. An active, stellar nursery, a star-forming nebula, right? So, do we see that in Galaxy C? Yes. Do we see it in B? Yes. Do we see it in A? No, right? No gas, no dust, nothing to make new stars out of, right? Elliptical galaxies don't have gas to collapse and give birth to new stars. So, no star formation, right? In elliptical galaxies, there's no new stars being born, which means this galaxy has whatever stars it has. And those stars are just, slowly aging and dying, but there's no new stars being born to replace the ones that die. Which galaxies have blue stars? I mean, that's a lot more straightforward, right? Blue stars in B and C, but not A. Which ones have red stars? Well, they all do, right? All of them have red stars. Old stars? Well, now remember, right? Old populations of stars are redder, right? Because red stars are cooler, and they're cooler, especially if you're talking about main sequence stars, right? On the main sequence, luminosity, temperature, if you're looking at main sequence stars, and most stars are main sequence stars, right? The red stars are the low mass ones, and they live a long time, right? These low mass, cool red stars down here have the longest lifetimes. So you're looking at an old population of stars if all the yellow, orange, and red stars are still alive, but all the hotter, higher mass stars are dead already, right? So, do you see populations of yellow, orange, red stars that live a long time? Yes. Yes, looks like there's some in there. Yes. Definitely some in the bulge at the center of the spiral. Yes. So why are there red stars in all three galaxies? Because those red stars are old. They live a long time. They're old now, and they're still going to live a really long time because these red, cool, low mass stars live long lifetimes. How do you know if there's young stars? Well, a young population of stars is blue. So if you see a blue group of stars, like these over here, right? These blue stars over here, these blue stars, that cluster of blue stars over there, or all of these blue stars, right? There's a whole bunch of blue stars in B over here, right? Why are those stars blue? Because they're hot, right? So those are blue, hot, bright, high luminosity stars. Why? Because they're high mass stars, right? They're high mass main sequence stars. And what do we know about these high mass main sequence stars? They have short lifetimes. So when you see a young population of stars, it's going to be blue. Not because all the stars are blue, right? When stars are born, they're all born as main sequence stars. So a young group of stars is going to have the high mass, the medium mass, the low mass stars, all of them. But the brightest ones are going to be the blue ones. And so when you see a blue group of stars like these over here, it's not that there's only blue stars, it's just that those blue stars are the brightest ones. And so they tend to dominate the light. That's going to stand out. You're going to see them most. and you know that blue group of stars, that blue population of stars, you know they're young. These stars have to be young because they don't live very long. If these stars were older, they'd be dead already. So when you see blue stars, like you do in B and C, you know they have to be young. When you see a population that's really red, it means the blue stars are already dead, the white stars are already dead, the yellow ones might be dead, right? And here, these stars are so orange, probably because only the orange and red stars are the ones still alive, and that means they must be really old. So, a picture is worth 1,000 words, right? Just taking a picture of these galaxies and looking at their shape, their color, you can get a sense of history, right? You see a blue group of stars and a bunch of gas and dust. They go together, right? That gas and dust collapses under gravity. It gives birth to star-forming regions, the red blobs. And then what comes out of star-forming nebula? Young new stars. Young new blue groups of stars. And so, like you see from your answers here, right? In a galaxy with a lot of gas and dust, you're going to find star-forming regions, and you're going to find groups of young, new blue stars. The elliptical galaxy doesn't have any of that, right? The elliptical galaxy doesn't have gas and dust, so you're not going to see star-forming nebula. You're not going to see young stars born out of those star-forming nebula. All you've got is old red and orange and yellow stars slowly dying. Very slowly dying because these low-mass stars, these red stars, live for such a long time. It's once we know the connection between gas and star birth and star life and star death, and how the deaths of stars feeds back into the gas that gives birth to the next generation of stars. Right? Once we know the connection between gas and stars, then we can zoom out and look at these galaxies to say, okay, how does this play out in the big picture? They go together. Gas and dust, star formation, blue stars, young stars, they go together. All galaxies, though, have old stars. Right? They may not be the brightest, but they're the oldest. They're the ones that live the longest. So even galaxies with young stars will also have old stars in there. Old stars left over from the previous 1 or 2 generations of star formation. Right? Just because a galaxy has some population 1 stars, it certainly means that there's still some population 2 stars still left hanging around. All right. So, with those tools under our belt, go for the practice. I'll give you some more pictures of galaxies, and you can tell me about those galaxies in the practice too. All right? Go for it, and have a good one.